Welcome back to Differential Calculus. This video is on the fundamental theorem of calculus. Of course, the fundamental theorem of calculus is something that I've introduced you in a previous video. I have it written here. If we have an accumulation function big F of x, the integral from 0 to x of little f of tau d tau, then the derivative with respect to x of big F of x is little f of x. We've already established this. We know how this works. But we haven't gotten into the power and why it is so important. So let me get my head out of the way and let me show you the biggest trick in calculus. I want to pick any two real numbers, a and b, so that a is less than b. And I'm going to think about big F of a, which of course is the integral from 0 to a of little f of tau d tau, and big F of b is the integral from 0 to b of little f of tau d tau. Nothing surprising there. And if I think about the graphical interpretation of the integral, I have some sort of a function here. I've got my point B. I've got, let's not do that in blue, let's do that in red. I've got my point A. And burying the lead, what I'd really like to think about is the integral from a to b of little f of tau d tau. Well, the integral from a to b is this part of the area under the curve. Big F of b is the area of all of this, and big F of a is the area of this much. Since they overlap on this part, well, if I subtract big F of b minus big F of a, that means that this part of the area gets canceled out, and we're just left with the area between the two values, which is the integral that I wrote down to start. This expression is also known as the fundamental theorem of calculus. It is the same theorem, just rearranged a little bit. I did a little bit of algebra. But look at this. Let me move that so I can actually stand here and talk about it while you can see it. The integral from a to b of f of x dx, because it was just a dummy variable, I could use x, I could use tau, I could use whatever I want, but it's big F of b minus big F of a. If I want to evaluate a definite integral, I look at my integrand. I find the function whose derivative is that integrand. I evaluate it at the two limits of integration. I subtract them. I don't have to do anything with Riemann sums. I don't have to do anything with geometry. I have to find an antiderivative. I have to evaluate it at a couple of points, and I have to subtract. Although that statement does get to the heart of the matter. How do you find the antiderivative? Let's take an example that we know how it's going to work. The integral from 1 to 3 of 2x dx. Right? That is a simple integral. I can solve this thing geometrically. I can sketch out the graph y equals 2x. I can look when x is equal to 1. I can look when x is equal to 3. The values of y are going to be 2 and 6. And I can calculate the area of this shape. It's a bit of a weird shape, but if you turn it on its side, you might have a better chance of recognizing that this is a trapezoid. The area of a trapezoid is 1/2 times the value, or the sums of the values of the bases, right? So average the height on either side and multiply by the distance between them. Well, the distance from 1 to 3 is 2. So we'll take 2 plus 6, we'll divide by 2, we'll multiply by 2, and all told we'll get 8. So I know what this integral should be. But I want to use the fundamental theorem of calculus. So I have to find an antiderivative. And I chose this one because, well, 2x is pretty easy. The derivative of x squared is 2x. All right, the notation here is a little bit interesting. It takes some getting used to. And I'll admit that the notation I use isn't quite the standard. The standard notation is to write down your antiderivative, write down a vertical bar, and put the limits of integration at the top and bottom. I find that that is a little bit messy, especially in some expressions where the integral isn't the only thing that you're dealing with. So instead, what I do is I surround the entire antiderivative with square brackets to make sure that I don't lose anything. But this notation is just telling me that I want to evaluate at those two endpoints. And then subtract. So 3 squared minus 1 squared, which is 9 minus 1, which is 8. Exactly what we said it was supposed to be based on the geometric interpretation. One of the troubling things about this whole process is that I need to identify an antiderivative. And I know that the derivative of x squared is equal to 2x. But x squared is not the only function whose derivative is 2x. If I took the derivative of x squared minus 9, well, the derivative of x squared is 2x. The derivative of 9 is 0, so it doesn't add anything to it. We just get 2x. Or if I took the derivative of x squared plus 5, I would get 2x. There are infinitely many antiderivatives of any given function. That's something we'll be exploring more in a future video, but for right now, you can try, right? Use x squared minus 9 instead of x squared and evaluate those endpoints. You'll end up with 0 and negative 8, and 0 minus negative 8 is 8. Try evaluating using x squared plus 5 instead of x squared on the endpoints. You will end up with 14 minus 6, which is also 8. No matter which antiderivative you use, you get the same value, and that's pretty amazing. Again, we'll talk a little bit more about why that's the case in a future video, but for right now, it is the case, and that's kind of enough. All right. So to wrap up on this one, let's look at one more for you to take a look at. How about the integral from 0 to pi over 4 of cosine of x dx? All right, a trigonometric function here. That means things are a little bit messy. But think through what you know about derivatives of trigonometric functions, and you should be able to find one of the antiderivatives pretty easily. All right, take a couple of minutes, see what you can do with that one, and I'll see you in the next video.